Okay, so this is one of my more favorite sections. It wasn't when I was your age, but it's turned into it. This section, we deal with what we call identities. Now, for everything that you have done to this point, you've dealt with equations. Now, equations usually hold true as long as the left side equals the right side. An identity is something that holds true that has been proven for absolutely every possible solution. Okay? So it always ends up being true. And what an identity does is it's like a formula in physics, let's say. It allows you to solve a question that appears to be more difficult. You put it into an identity and then it simplifies it for you so that you can get it. The long and short of it is this, is you are working with your unit circle to solve for specific angles and getting exact values. Now if I say to you, what's the sine of pi over 6? You're going to tell me 1/2. That's an exact value. What's the cos of pi over 6? You're going to say root 3 over 2. That's an exact value. Pi over 6 is 30 degrees, right? Well, one of the angles that's not on the unit circle is the sine of 15 degrees. I want to know the exact value. So we want to be able to solve it without the use of a calculator and get an exact value. Well, in order to do that, you have to use an identity to show you how to get to the sine of 15 degrees using the sine of 45 and 30, let's say. Okay? So the first thing that you're going to do this morning is you're going to copy down a number of the identities that we start with, okay, that we use. All right? So to begin with, we start with our reciprocal identities. So cosecant theta is 1 over sine theta. Secant theta is equal to 1 over cos theta. And cotan theta is equal to 1 over tan theta. Tan theta is equal to sine theta over cos theta. Cotan theta then is equal to cos theta over sine theta. Now these are the very basic ones. These are the 6 basic ones, 5 basic ones that we began with, that we have worked with so far. Okay, and we've just used these, and we've always talked about them as being equations, but we're going to call them identities now. Because what it means is that no matter what angle I put in there, the values will always equal on the left side and the right side. All right? These are the new ones that start with Pythagoras' theorem. Okay? So I just want you to take a peek at that unit circle, that circle on page 188 right now. So we call it a unit circle because it's a radius of 1, right? And you notice that the x value is the cos of theta and the y value is the sine of theta. So using Pythagoras' theorem, the first identity we deal with is cos squared theta plus sine squared theta is equal to 1. Now this is probably the most important identity you're going to work with. And the reason is it allows you to convert from cos theta to sine theta, or sine theta to cos theta, using this identity. So if you know one, you can convert to the other, because the other is just 1 minus, for example, cos squared theta is 1 minus sine squared theta. Okay? Now, we're going to create 2 more identities from this. And in order to do that, I'm going to, first of all, divide everything by cos squared theta. Okay? So I don't want you to write this down. I'm just going to show it to you. So I start with this. Cos squared theta plus sine squared theta is equal to 1. Now I'm going to divide everything by cos squared theta. As long as I do it to everything, all right, I'm okay. okay to do it as long as I do it to everything on the left side and everything on the right side. So what does this equal? Well, what's cos squared over cos squared? 1 plus. What's sine squared over cos squared? Okay, look at your identities right now that we wrote down on the sheet. What do you suppose sine over cos is? So that'll be tan squared theta, right? And that's equal to what's 1 over cos squared theta? No, secant. Secant squared theta. Okay? So there's your second one. Alright, so there's your second identity. I want you to write that down. 1 plus tan squared theta equals secant squared theta. Okay? Now I'm going to do the same thing, beginning with my Pythagorean identity, and I'm going to divide by sine squared theta now. So cos squared over sine squared is cotan squared theta plus 1 equals cosecant squared theta. There's your third one.
Excuse me for the interruption. America, Montiel to the office, please. America.
Okay so far? So, right now, we're basically, the analogy I use is you're putting your physics formulas down. We've done that before, where we list out our physics formulas, and then we plug in information into the formula and solve for the unknown. You're more or less using identities to do the same purpose. Okay, you're trying to make the questions easier by using these identities. Alright, so first thing they want you to do is they want you to understand how it works, how an identity works. So determine the non-permissible values in degrees for the equation cosecant theta equals cotan theta over cos theta. Okay. Cosecant theta equals cotan theta over cos theta. All right. Now, the unique quality about these is normally when I do non-permissible values, what is it that I can't have? A zero where? In the denominator, right? So that occurs here too. But you notice that you have, for example, cosecant theta is what? 1 over sine theta, right? So therefore, sine theta cannot equal 0. So now I have multiple values, because if I continue to go around the circle forever, right, I'm going to have values of sine theta equaling 0. So the first thing that I do is I say, okay, sine theta can equal 0. Therefore, theta can equal. All right. Where on the unit circle does sine theta equal 0? Where's my y value equals 0 on the unit circle? 0 and
1, 1, 2.
No. I'm asking you for an angle right now, right?
90.
Not 90 though. Not for y.
Not for y.
180, 360.
Right. So it gives it to us in, it says in degrees, right? So we can use that. So what is it? 0, 180 degrees, 360 degrees, and so on, right? Okay? So how do you actually show that? If I wanted to show that it goes forever?
10, 5.
Yeah, that's right. Okay? Except I'm going to use, because I have 360s, right?
Yeah.
Okay? So I'm going to do, and it occurs every 180.
So n is 180.
Yes. That's
it.
Yeah, 180 degrees and integer. Right? So 1, 182, 180 is 300, and so on. And so that would be, yeah.
You have to have that in squiggly bracket.
Yeah, you do.
So
Because it's a domain, you need to show it in squiggly brackets.
So if I did that without the bracket, That's what I do for.
use a half a mark. Yeah. So you wanna, and I'm not so concerned about our tests as I am the exam. The exam, we have to really be crisp on our notation. That's one of the things. Okay, now the only time that you don't need it, I believe, is if they would put theta and a blank. All right, but my expectations are that you need it all the time, so we'll work towards that. Okay, so now, that was for this guy, right? But I also have cos can't equal 0 degrees either, right? It's on the denominator of a fraction, agreed? So now, theta equals, where is cos?
90 and 270.
90 and 270, so how do I show that then? Any ideas?
Well, you need the odds, so
92n plus 1.
Say that again?
92n plus
plus,
1.
no, it'd be plus 90, wouldn't it?
Okay, so 90, you need to, okay, let me actually show you an easier way to do that. Without the plus 1 part, 2n plus 1. What if I said this? What if I said 90 degrees, right? Plus exactly that. Would that not be right?
Yeah.
Because I add 180 to get to 270, then another 180 to get to the, with a 270 and 180 would be 450, right? So if I just put this exact thing here now, so 180 degrees n, where n is an integer. That to me is one of the hardest things for grade 12s to do, is write out those. Okay, now, so far so good, right? Okay, so that's my non-permissible values. And that's all that that A part asked you to do. Find your non-permissibles. Now, when you have cotan and tangent, you have to know which one's on the bottom because you'll have to include that too. So in this case, we already covered cos and sine, but if you didn't have one of them there and you had like tan with the cos on the bottom of the fraction, so you need to know that. But you'll see as you go. The problem I have with this section, in the old days when we did this, we hammered out like lots and lots and lots of these identities. In this one, they just kind of skip them and they skim them. All right, so this newer course doesn't give you enough, and realistically, the more you can do it, the easier it becomes. All right, it's not a difficult thing, but it's hard to see these identities. Anyways, okay, so it says numerically verify that theta equals 45 degrees is a solution for the equation. Okay, so now, the first thing that you need to know about doing these identities is you never, you never use equals all the way through. An identity is not an equation. It means that that side stays the same as the other side. It means they are exactly the same. So in this case here, cosecant theta equals cotan theta over cos theta, right?
Yeah.
Okay, so here's what happens. You write your original statement with an equal sign. And then you draw a line where the equals is. All the way down, and you generally only work on one side. But because you're proving this one, you're going to work on both sides. Okay? So here's what happens. I draw my line straight down. I do not put another equals on there until the very end. Okay? So what is cosecant theta equal to?
1 over sine.
1 over sine theta. Okay, so you have a choice now. At this point, I could substitute in my 45 degrees and I could solve this. So let's do that. So that gives me 1 over, what's the sine of 45 degrees? Yes, it's root 2 over 2. Right? So then that makes this 2 over root 2 on this side. Okay, so far? All right? Cotan of 45 degrees.
1 over tan theta.
What, okay, yeah. Or, okay, let's do, I'm going to show you what I should do is just substitute my values, but I'm not going to. So what I have here, when I work with COTAN, when you do identities, one of the procedures that they tell you to do is change everything to sine and cos as quickly as you can. So I'm going to do that right now. What is cotangent theta? Cos over sine? So I have cos theta over sine theta over cos theta. Agreed? Right? Here's my cotan, and then I've still got my cos here. So that's the same as saying this. Cos theta over sine theta times 1 over cos theta. Right? So then I would go just like that. And what am I left with? 1 over sine theta, which is exactly what I had here, right? So at that point, I'd put my equals in. But I'm not done yet. I want to show this. So then that is, I've got 1 over sine theta, which is 1 over root 2 over 2, which is 2 over root 2. And now I put it down here. My last statement has an equal sign. Now normally, I only work on one side of an equality statement. Or an identity statement, not equality statement, but an identity statement. I only work on one side, if at all possible. But right now they asked you to prove that the left equals the right, so I needed to work on both sides of it. Okay? Paying attention here, guys? Okay? Alright. I'm not going to do the graphing part just yet. I want you to look at page 190. Any questions about that so far? And that one was set up to prove using angles. We don't, as we get going, just today, they're just showing you that an identity is exactly the same on both sides, that the angles will always be the same. The exact values will always be the same. Okay? So, here's one here. They want you to simplify this expression. So we have tan x cos x, secant x, cotan x. So the first thing that you do when you simplify an expression is write in your non-permissible values. Okay? So in this case, just looking at it, it's the same idea. Sin x can equal 0, cos x can equal 0. Okay? Then you should write the angles in. So this time, last time we did it with degrees. So let's do it right now with x can equal, let's do it with radians. So I want you to just think back to the last question, or the 2 questions ago. What did we say the non-permissibles were? 0, 90, 180, 270, 360. We covered all of them, didn't we? Right?
Pi over 2.
Yeah, 100% right. Pi over 2, n, where n is. Well done, Casey. And that covers all of them, right? Every 90 degrees. Okay, so there's that. Now I want to reduce this. So what was the thing I just said 2 minutes ago?
One, okay, cos and sine.
Change them to sines and coses, right? So tan is sine x over cos x, right? This is cos x up here. Secant is
1 over sine.
1 over
Cos
x, right? And cotan x is
over sine.
cos x over sine x. So I've done that. And now I just want to simplify.
Can we cancel all the coses?
100%. Cancel, cancel. Cancel, cancel. So what am I left with here?
Sine over 1 over sine.
Well done. Sine x over 1 over sine x, right? Which is actually what?
Two sine x.
Sine x
No,
squared.
it can't.
X squared, yeah.
Sine squared x.
I gotta multiply by the reciprocal of this guy.
Oh, right.
So what is it gonna be equal to?
Sine squared x.
And there's your solution. There's your simplified value. Okay, so far? Okay. Now, I'm gonna ask you, I'm gonna change the question from the book. And the question now says, simplify this expression, and I want it in terms of cos. So what is sine squared x in terms of cos?
Wow. Cos squared equals 1 subtract sine squared. And
You're on the right track. Okay, so now, pull up my identity sheet, right? And I want to isolate sine squared x. What's sine squared, or sine squared theta in this case, right? What's sine squared theta equal to?
1 subtract cos.
So if I asked you that, you would say, okay, well then this is 1 minus cos squared x. And we simplify it. Okay, so that's what the point of these identities are. Right? That's the idea behind this for right now. Okay, so far?
There's no like active numbers. No most part.
Nope. No substitutions on this one right now. Okay? All right, let's take a look at that working example 3. So it says verify that the equation, so I've got cotan squared x minus cosecant squared x is equal to -1. And then it says, just prove that it's true for pi over 4. So in this case, I would just simply substitute in pi over 4. And then I would change the sines and coses and go from there. But I don't want to do that right now. I want to show you how you should approach this. So the first thing I do is write out my main statement with an equals, and then I draw a line down. So I want to prove now that that is equal to that. Okay? So I want you to pull out that identity sheet right now. And on it, I want to change it so that either they're both cotan squareds or they're both cosecant squareds, depending on which identity you want to use. So look at your 3 identities. Is there a possibility that I can change it?
Cotan squared plus 1 equals
Just-
cosecant squared.
Okay. So say that again.
Could you use cotan squared theta plus 1 equals cosecant squared theta?
Okay. So you want to substitute in cotan squared theta plus 1 for the cosecant squared?
Yeah.
Okay, sounds excellent. Cotan squared x minus cotan squared x plus 1. Right? Just a simple substitution at this point. Another point of emphasis, anytime I do a substitution off of an identity sheet, okay, now you get these identities on your exam. It's part of your formula sheet. Put them in brackets. That signifies that you understand that you had to put that in for it. Okay, so, and you've been taught that right from day 1. Since grade 10, I've been teaching you, if you substitute in, put whatever you substitute in brackets. Now it's necessary that you do it. Because your mark is now graded on steps when it comes to identities. Alright? It's not the end game, it's everything in between that you get marked on. Alright, so now at this point, I get rid of my brackets, and what happens?
-1.
It becomes -1. And so what I do is I go like that. I've proved my left-hand side equals my right-hand side. The last statement needs an equal sign, and generally, I just make it, I could put it as -1 equals -1, but I like to put it as -1 equals right-hand side or left-hand side, depending on which one I worked on. Okay, so far? All right. That's basically it for today. Okay, so I need you to work through them. The problem that you have in this is they're time consuming. They take time to do these questions, so you have to work quickly and don't feel that you have to do every single question. Once you get into a rhythm and once you know what you're doing, get to the next section, do the next question. Alright? Okay, so that's it. You can take the rest of today, you got 40 minutes or so to work on that. Tomorrow's lesson?
Yeah.
No,